Hopefully we can switch back to that one later. Hey, Nelson, let me know if you can hear what's going on in the classroom.
Yeah, I can hear you.
All right, so the last thing I need to do is be able to show my screen.
I can see your screen now.
Okay, you can see the computer graphics fundamentals screen?
Yep, can see it right now.
Okay. All right, so the nice little microphone that clips onto, somebody didn't seat it all the way in, so we got to wait for it to charge a little bit, and then I can like not feel like I'm a DJ up here. So anyways, I just want to welcome you all to Computer Graphics Fundamentals. I need to mute that. Okay, I think my computer just needed to be muted. So, turn off YouTube. Okay, so all right, once again, welcome to Computer Graphics Fundamentals. Let's make sure that you want to see me all day. Okay, I think we got everything going. Well, Okay, I think we're okay. All right, so hopefully we're trying to work out the bugs on day 1 so we don't have bugs on day 2 and day 3 and day 4 and day 5. Okay, so we're going to talk about a little bit what the course is about, go over some of the elements of the syllabus, and then we're going to start out on doing a survey on computer graphics. The feedback I got from teaching previous courses that it's helpful to kind of know kind of the broad brush of what's out there in computer graphics. So you kind of know, well, what are some things I can actually work on rather than kind of get halfway through and still kind of have a vague idea of what topics are interesting. So that's the 3 things we're going to go over today. If at any time you have any questions, just slip up your hand and we'll go ahead and answer it. And if you have any feedback, comments, you feel free to like the class to kind of be open for participation. Essentially, what we're going to cover in this main course is some of the fundamentals in computer graphics, things like how we perceive objects, like color and so on, how you represent signals like analog signals in terms of discrete samples, because we all know that computers don't work with shades of gray, they work with zeros and ones. It's got to be like all on or all off. So we need to be able to change how we represent things in real life to suit a display. And then we're going to start talking about 3D mathematics, probably starting next week. So we have a chance to kind of go over all of the, like I said, survey what there is to work on in computer graphics. And then we're going to get into what I call these kind of 4 main things is rendering. We're not going to get too much into advanced rendering like you might see in the Unreal Engine or Unity engine, but we are going to, give you enough information that if you were to sit in on a discussion on advanced rendering, you wouldn't be like, I have no idea what they're talking about. Okay. And then we'll go over modeling, because you can't have 3D graphics without 3D models. And right now, ray tracing is the hot new technology in computer graphics. How many people don't know that? How many people never heard of ray tracing? Okay, NVIDIA has done their job. All right, so ray tracing is in. They want to sell you new graphics cards, and it would you would be in terrible shape if I didn't teach you how to do it. All right, so we're going to cover ray tracing. I think in previous years, ray tracing might be the kind of thing that you get in a more advanced course, but I think it's almost a necessity nowadays because you decide to go work on something. Even in games, you're going to like, well, what do you know about ray tracing? All right. And then sprinkled throughout the whole course is game design, because I figure we might as well make computer graphics fun. Like, it's already fun just putting images on the screen. It's even more fun when you can make it do things that are interesting. All right. So let's go over the syllabus a little bit. And I'm going to try and get to Blackboard from here without blowing this up. So share Blackboard. Okay. It's weird because on the back screen, I see myself. And on this screen, then I see what I actually want to look. So I'm getting confused with the misinformation over there. All right. Okay. So syllabus. So I guess just by way of just how this course is structured in Blackboard, we have announcements. So if I need to send, hey, your homework is delayed by a day, or we're going to do X, Y, Z activity in the next day, or maybe a clarifying detail for something, that'll show up in the announcements, and everybody should be getting an email for that. So hopefully that's kind of automated. You'll notice that there's I have the Zoom and YouTube live stream links over here. So there is a noticeable delay of about 5-10 seconds for it to stream on YouTube. And I don't know what the delay is on Zoom, but keep that in mind if you're trying to ask a question. There is a hand raise feature on Zoom. So this is more for the students in Anchorage. So if you need to say, hey, I've got a question, it should put a note, an alert on top of my screen. Okay. And then after that, we have syllabus and resources. So I have a bunch of links to one is a link to the book. One's an online book, it's free. And the other one is a requirement for the course. So this is the real-time rendering 4th edition, just came out in the last year. Really good, really, really good. So we're gonna have reading assignments out of this book, and I'm trying to base as much of the course material on the information in there. And for nowadays, I mean, if you want to do any kind of real-time rendering, I think that book's got you covered. It's gonna give you a good survey of what techniques are out there, what papers they're kind of in, and it's pretty good. Let's see here. Okay, so the syllabus, I'm gonna open up syllabus. I'm gonna open up the 484 syllabus because the 684 is for the grad students. It's pretty much the same thing. There's just a few extra details grad students will have to do, but I'll point it out when we go through the 484 syllabus. Okay. Hopefully everybody can read it. Okay. All right. So just by way of introduction, I'm Dr. Jonathan Metzger. I'm originally from Albuquerque, New Mexico. I've been in Fairbanks for about 2 years now. Started teaching January of last year. So fairly new, but I'm starting to get the hang of it. So that being said, if you have any comments or suggestions or improvements that I can make, I'm definitely all ears because I would like to make the experience as valuable as possible for you, because you guys are shelling out all the big bucks for the classes, and I want to make sure that the class is providing value for you guys. So if it's not doing that, please feel free to reach out to me. And office hours are Monday and Wednesday. It's also Monday, Wednesday, and Friday. I kind of divided them up a little bit so that the CS 201 course has their time in the morning from 10:15 to 11:45, and that we have at least an hour on Monday and Wednesday before this class. So generally I have an open door policy. So if you come by my office and doors open, then feel free to stop by. And if you have any questions, you're more than welcome to come on. All right, the prerequisites for the course, CS 202 and Math 253. This is just to make sure you have a little bit more mathematical maturity and that you've completed your main programming course for the first year. I'd like the course to be, I know there will have all different kinds of skill levels in here, but I figure there's no reason why we can't try to get everybody in the class. So we're using Blackboard for just about everything. And the final is going to be in December, kind of late this year, I think, Monday, December 9th. So the book, Real-Time Rendering, I think that's a requirement for the course. And I think that you will not be in good shape if you do not have the book. And then Ray Tracing in 1 Weekend by Peter Shirley is a free book that you can get on GitHub. And we'll be using that later in the course when we start talking about how to implement a ray tracer. Okay, so the basic description of the course is that computer graphics is a big field. It ranges from like human computer interaction to virtual reality to graphical user interfaces. 3D modeling, computer-aided design. I mean, just about everything that you use on your computer involves computer graphics of some sort. It literally touches every element. And this is one of the reasons why it's a critical piece of understanding in your computer science field. So I'm glad that you decided to take a more in-depth look at it because it is very exciting. Okay, so some of the outcomes, we want to, understand this term digital presentation, right? So like we said, the computer doesn't deal with gray, it deals with black and white. And so we have to find a way of how can we take that black and white and turn it into something that doesn't feel black and white to the user. We want to interact with it in a analog kind of way, if you will. So part of that is just understanding how do you represent analog signals with discrete samples and what are the complexities behind that. I figure we should, I haven't done this in the past, but I figure it would be a good idea to do that, how to implement user interfaces in computer graphics. I think that's an important need rather than just relying on, the W key does this in my program, and then you forget 3 months later what it was supposed to do. Being able to describe color models, these are some basics that we should be able to do. There's different kinds of color models. Work with three-dimensional mathematics to move things around in space. And then we start branching off into the actual, some of the more visually appealing things like, how do you simulate light transport in a computer? How do you make something look like it belongs in the real world? And then kind of going along with, okay, on top of that, what kind of, on the programming perspective, what do you use to actually put graphics on the screen? And because I like game design, I figure I'm just going to wrap that in this course just because it's fun. Okay, so there's, as far as grading goes, we have 2 exams, a few homework assignments. Well, it's going to feel like a lot of homework assignments, but I'm a big fan of the more you do, the more you are able to do it. Brian Kernighan said, programming is learned by writing programs. So we're going to try and do that as much as possible. All right, so 40% of the grade is homeworks. 15% is a research project, which we'll talk about in just a moment. And then 5% is class participation. And that class participation is essentially, I'd like everybody to be a participant. So I'll have you all look for interesting computer graphics news or articles that you can share. Something short, that takes 2 minutes to explain. And we'll have one person do that. And you'll do it up to 2 times during the course. I think we have a small enough class, everybody will have a chance to do it 2 times. And that way we can kind of all participate in the learning. All right, let's see here. Go back to the the slides over here. All right. So the homeworks are basically going to be designed to, they're part question and answers, part design of an actual computer graphics program. And this gives you a chance to kind of get experience. All right. And I'm going to show you a template that I have that we're going to kind of work with for doing what I call a homework report or a project report. So I'm a big fan of using LaTeX. Those of you who taken my class before probably know what LaTeX is, but how many people don't know what LaTeX is? LaTeX. Looks like latex, but pronounced LaTeX. Okay, maybe people have heard of it. So it's basically a typesetting language. So people who write books like this, well, they don't use Microsoft Word to write books like this. They'll use an actual typesetting language, and this gives us a chance to get familiar with how you do technical writing, scientific writing in the computer graphics field. So we're gonna do that. And to make it easier, we're going to use Overleaf, which is a website that basically handles all of the compiling and everything that goes into that. Makes it pretty easy. And the homeworks have a few different components. So normally you'll be asked to do, I guess, the main program, the main part of the program. So, for example, one of the first homeworks we're going to do this. We're going to participate in 1 hour game jam, which is a game jam designed to kind of make simple games in about an hour or so, which really means a couple hours because it's not easy to just kind of jump into it. But this gives you a place to talk a little bit about design, a little bit what happened, what went right, what went wrong. I'll have some questions. There might be some math problems, or they might be computer graphics topics related to the reading. All right, a screenshot so we can kind of share the work and make sure that we're all following software development fundamentals. So using GitHub for hosting your repository, and there may be a few more requirements beyond that, but trying to make it so that the homeworks don't take more than about 4 to 6 hours. You should be able to, if it's taking you more than that, then please talk to me so we can get that figured out. But the goal of the homework is just not to drive you into the wall with meaningless stuff, but to actually get you some experience with computer graphics. So here's some examples that I like. I've always been a fan of postmortems, and gamasutra.com is a big game design website. And let's pull this up. I have to share that screen. Okay, so it's basically developers of big games, like say Spider-Man's from 2002. They would actually publish this in Game Developer magazine, and I'm looking for like a paragraph, okay? But this is a good, you read these and you get a clue into what goes into an actual large design of a project. It takes, a lot more people, things that you would probably, after you're done with college, I imagine you want to be part of a software development team somewhere. And these kind of explain all the different things that happen in the course of a development cycle. So, they'll talk about things that go right, things that go wrong. And this is good information to kind of look back when you reflect on a project that you've just done and find out, okay, what helped me get better and what didn't help me. And these are the kinds of things that then you can share with other people and say, yeah, I really learned that if you do this, it'll make it go smoother. Or if you do this, you're in for some bumps. Okay. And the second thing is like design documents. So sometimes it's good before you start on a project, just kind of spend some time thinking about, okay, what am I trying to accomplish with this? It's the same reason we ask everybody to have some kind of plan for going through college. All the courses you're going to take, when you're going to take them, and that kind of gives you a clue of what kind of education you're going to get at the university. It's always good to have a plan. Things that are written without a plan, sometimes they work out, sometimes they don't, but it's always good to at least have something to kind of work on. So there's a few links over here for, say, Wipeout. It's a 3D game that came out for the PlayStation. Another one's called Rogue Legacy. And you'll see that these are pretty substantial documents that are regularly produced in the industry. Okay, so let's talk about the research project. So research project is called A Journey in Computer Graphics. So rather than have just a plain, project that you kind of work out, I thought it would be interesting to have one where the theme is can we come up with some kind of like historical journey? So like riding down the Colorado River, for instance, or driving, going through the Alaska Range, or some kind of journey. That way you kind of have to plan a story that you're trying to tell. And you'll find that as you get, go into your careers, there's a lot to be said about how do you tell a story to people. And it doesn't necessarily have to be a historical story, in the real world. It might be, okay, how do you communicate the goals of our company to potential users? And you'll find that nowadays, websites more than ever, or even companies, how can they be personal to the user? What makes it more useful to them? And so part of this exercise is to, okay, let's come up with let's see what all the different journeys that we can come up with in the class. All right. So the idea here is every one of you will have a research project, and there'll be some historical journey, and we'll just say up to 1900. We'll just you pick something interesting that you find. It could be Marco Polo's travel to China, or any number of Oregon Trail is probably one of those classic examples of a journey that anybody not played Oregon Trail? All right, so everybody's like knows that one. Okay, so I think this is interesting. So this first week, and I'll talk more about it on Wednesday, but we want to do an author bio. So I figure the first week is where you start to iron out all the kinks, like what's going to keep us from like making progress in the course. So we'll start out with some simpler things that are that it's not graded, so you don't have to worry about losing points, but you get all the things done, and that'll make sure that you won't have any problems with the homeworks later on and so on. And then after that, we're going to do a pitch. So I always like the idea of, can you do like an elevator speech about the project that you're trying to do? So the first thing that's coming up, I would want to say in the third week, is a pitch. So you do a 1-minute pitch about what your journey is all about and what you hope to accomplish. And then there's a proposal. So this is where you've had a chance to think about what you actually want to do. All right. So you'll kind of decide, here's how I want to go ahead and implement my program. And then we'll have a number of updates along the way, so you can kind of post progress. And you'll just put a few, like a screenshot or a few things like that to kind of talk about how you're making progress through the, this is to help you avoid the last minute phenomenon where, and I'm totally guilty of it. So I'm, then you can never like do as much as you'd want to if you're up against like a 12-hour wall of time. So this is just to kind of help make sure that you have a chance to communicate to everybody, or to me. You can share this with anybody you want, but to communicate, how are things going? This is a great way to catch problems up front before they become real problems later on. And that's all kind of working towards a state of the art. So state of the art is, anybody ever try to solve a problem? You hear about a problem, you're like, oh, I know the answer. Yeah, you jump in, and then you find out a couple of months later that there was, somebody had already did this work before, and you didn't have to like spend 2 months wasting time. You could have just like got the one thing and been done in an hour. And I think it's part of human nature to just kind of want to jump in and like, oh, let's solve the problem. Problems are exciting. We like to figure things out. And so one of the things about state of the art, this phase, is we'd like to find some kind of graphics problem that we need to solve before we can, that's going to be a critical part of our journey program. And then after that, then you'll just continue working on your program, and you do a postmortem at the end, just kind of say, okay, my development's done. Here's everything that happened. And then you'll give your final presentation the last week of course, where you can show everybody all the work that you've done. Any questions so far? All right. Just to help out here, I'm going to go back to the web browser. Okay. All right. So just so we can see the schedule real quick. So this is more or less how I have everything kind of situated. So this weekend we'll have like a homework 0 and the author bio for the report. And more or less we'll have like 1 or 2 things due at the end of the week. And generally I let you have until Sunday evening, midnight to go ahead and finish these things up. And if we need more time on, if we need more time to work on one of the homework or something, I have no problem moving things around. But if nobody tells me things need to be moved around and there's not a like, then it makes it hard to kind of adjust these things. So it's better to kind of, I guess, raise the flag before it's at the, you know, you're up against the timeline there. Okay, so I'll let you guys can look at that online, the schedule. The course policies. Essentially, you should come to class every time, and I'm not going to drop you if you miss four meetings. But if you are missing that many classes in a row, you should probably come talk to me so we can kind of figure out, you know, what's going on, what might be hindering your ability to come to class, or maybe it's just not interesting anymore. But that way, it's not. I've had a few students over the last 2 years where they just kind of disappear, and then you never see them again, and then you wonder, you know, you missed the midterm, and you know you missed a few other things, and you know, what are we trying to do with the course at this point? So I'd rather it not come to that. So if you're struggling or something, please come talk to me. And of course, the university has a lot of different policies. The department has a lot of different policies. The general, I like listening to a guy on YouTube. His name is Brian Lunduk, and he used to work for Linux Journal. And he has everybody's been doing, policies on how we treat each other. You know, that seems to be big in the last few years. And I kind of like his. It's nice and short. You know, be excellent to each other. And so, you know, the idea here is, you know, we all want to solve the problem, but we don't want to be a problem to other people. So we want to just kind of treat everybody with respect and kindness, and just try to work with each other to kind of help solve problems. And that is my policy to you. My goal is to help you succeed in this course. You know, that I want you to get the most out of it. All right. So computer graphics survey. All right. So, so for the rest of today, so we have about an hour, I want to just kind of talk about what there is to know in computer graphics. Just kind of throw all the words at you. And it could either turn out boring or it could turn out interesting. I hope it's interesting. So here's what I would encourage you to do. If you see something on the screen and you want to know more, say, please tell me about that, because that is what I want to work on. Or that looks interesting, because I'd rather, you know, rather we dig into what these things are rather than just mention them. All right. So just kind of raise a hand. How many people are in the class because they are interested in a particular computer graphics topic? Okay, a few. I bet everybody is. Okay, maybe we could just kind of, I guess, go around the room and just kind of, we could probably put them up on one of the boards. Let me see. Power, right projector. Okay, I want that one on. So we want the left screen. Markers. I'm going to see if the other microphone works, because it's kind of weird to. Looks like I got to write with one hand, hold the microphone in the other. All right, so I guess we'll just Nelson, if you can post your topic, like what you would like to do in the group chat, if you can, in the Zoom group chat.
Yeah, I'll do that.
Just type it in, and then we'll go around the room and we'll just kind of get a list of topics. So as you introduce your topic or the thing that you're kind of curious about, just go ahead and mention your first name and then what topic that you're interested in. So we'll start over here. All right. World building. All right. Thank you, Daniel. Levi, good user interface design. All right. I'll just work. Animation. All right. Biomedical imaging. Ray tracing. Procedural generation. Simeon. Okay. Put 2 over here. So we had 2 for graphical user interfaces. Gotcha. So how do you make 3D things look 2D? Well, how does a 3D object, how do you make that, put it on a 2D image? All right. That's kind of the science of projection. So projecting 3D to 2D. All right. Game design. All right. So and Nelson. Computer, let's see here. Nelson, are you interested in computer vision or?
Computer vision more so.
Say that one more time.
Computer vision.
Computer vision. Okay. We will definitely address some computer vision topics, even though sometimes that might be more of an artificial intelligence type thing. But there are some, image filters and different things like that. So definitely part of the whole computer graphics purview. All right. So yeah, so world building. Now, when you say world building, are you talking about like how you design levels, or are you talking like how do you create like massive worlds to explore? Okay. Yeah. Definitely. How do you make a more interactive, 3D interface? That is definitely really, really big. And especially now because, I don't know. Everybody here at least know of, Zelda Breath of the Wild. Okay, everybody's generally familiar. How many people have not played it yet? Maybe one person has not played it, but they've seen it, no doubt. That's Nintendo's really proud of it. But it's one of those like, yeah, you can do a lot of things in there. There's a lot of like interactive components, and it's one of the best 3D worlds that I've experienced. I think as far as computer games go, but yet when I go outside and I drive down the Parks Highway or towards Glen Allen or something, you can't help but notice that however far we've come along in computer graphics, we have not gone far enough. It's just nothing really compares to the real world in terms of how you can interact with it. We're closer than I think we've ever been in terms of the experiences that we create, but we're still not there where somebody would say, nope, not in the real world. I can tell that, and the reason why that's important is because part of computer graphics has always been, how can I get somebody to experience something they've never experienced before? How can you see something from somebody else's perspective that they've never seen before? Whether it's, imaginative, where you have to use a lot of imagination. Okay, I won't lie. Oregon Trail is fun, but I don't think that it quite captures the experience of actually being in a covered wagon going up and down the hills. I mean, I'm going to just say that it probably doesn't really fill that niche. But on the other hand, in not having played the game, if I had never played the game before and I had never studied it from a historical perspective, I wouldn't even think about fording a river, or going out hunting for food, or the realities of death and sickness, that are present on that way. Never would have really thought about it. So from that perspective, it's very successful because it gets people to think about what are some experiences you may never have had before, but you get to at least have a taste of it. And I think that now, if they were to make like an Oregon Trail with the budget of Zelda, I think it would be a different experience. And people would be, wow, this is something. So, I can get exactly what you're saying with world building. How do you take the physical processes and make it more something you can experience? Okay. A lot of people are interested in user interface design. So this is something maybe that you wouldn't necessarily get in a graphics class, but it totally makes sense to talk about it, because how you interact with the computer is one of the killer applications of computer graphics. One of the pioneering efforts of computer graphics was just being able to use a pen on a display screen to interact with the computer. I mean, that was, when people saw that, they're like, whoa, this is interesting. Using a mouse as another way of interacting with a computer that kind of changed how things, how people use it. Probably touch screens are kind of a big thing nowadays. Being able to, people want to interact with the devices, but they don't necessarily want to like pick up a piece of glass and metal. This isn't about just picking up a piece of glass and metal. It's about experiencing something that they wouldn't be able to experience. For example, I like music synthesizers, like analog synthesizers that you can kind of make new sounds with, electronic sounds with. And there are certain kinds of synthesizers called modular synthesizers where you actually use cables to kind of plug different modules together to get different sounds. And, if you were to buy one of those things for real, I mean, you're spending thousands of dollars just to kind of do that. But you can buy apps nowadays on a phone that allow you to kind of experience that without having to spend, your like life savings. And I know college level, your life savings is not very much. You're still kind of working on that, but so it's definitely important there. Just having some important principles of like, okay, well, how do you design something somebody will want to use again and again? How many people use a user interface and been like, this is just the worst thing ever? Anybody? I see a lot of smiles around the room. It's almost like how many people have had a bad meal, and you're like, yep, never eating there again. And that's exactly how user interfaces are. Some are designed to kind of make you happy, In other words, you actually like, yeah, I got some work done. This is good. I actually feel good about this. Rather than like, man, I wish that was over with. A while ago. Animation. I know animation's really big. Animation is sometimes subtle, but also kind of in your face, right? We all know things like, we call it in your face animation is like Toy Story, where you're like, you go to the movie and you have the biggest screen possible in front of you and you just want to see 3D characters dancing on the screen or playing out something. But then there are other kinds of like animations as simple as like, what if you just smooth scroll your web browser up so that it's not like jerking, so animation kind of covers all the way from the subtle to making user interfaces kind of feel smooth and organic, or all the way up to character animation or 3D movies and so on. All right. And that just helps you tell the story better, I think. Biomedical imaging, that's a very big one. Anybody have an MRI before? Hopefully not too many, but it looks like a lot. Okay, more than I thought. So I have some imaging of my knee that one of these days I keep telling myself, okay, I need to download that and try to load it up and see if I can like do a cutaway or drew marching cubes or something and kind of make a 3D model of my knee just to kind of see what it looks like. But think about how much that's changing how we understand about the human body, or how we can create new techniques like surgery. It'd be nice if we could like train every surgeon before they kind of get in there and start working on you. Or what if there's only a few people who know how to do a particular kind of surgery? Being able to kind of do that remotely, that's kind of interesting idea. All right. So then we have ray tracing. Ray tracing is, like I said, is big right now, partially because, our hardware is so fast that it doesn't take much to, we can kind of get back to what they kind of envisioned in the 1980s. And, it's useful for generating more realistic reflections and any number of things. But when it comes down to it, it is still the best way of producing a computer graphics image, because you're actually simulating the fundamentals of light. And that has been the best way of producing what we, see in the movies. But it would be nice to do it if we could actually like interact with it on our computers. Procedural generation. This is a favorite topic of mine. How do you generate content when maybe you're not an expert in the content? And this could be like a huge time saver. Like, how do you make, we talked about world building, but, could you generate worlds that have never been seen before that are plausible? And procedural generation is one of those techniques. I think, it kind of aims for, can we generate things that feel real, but using a mathematical formula, essentially. So how do you combine the, well, math is not simple, but it's a far simpler representation than say real life is. So how do you use mathematical techniques to generate 3D models or texture mapping or levels? Then we have some of the just basic mathematics, right? So projection. We're going to talk about that in the next couple of weeks. And then the last two, game design, computer vision. So computer vision is really big in robotics and artificial intelligence. It's pretty important nowadays. And game design is just, it's fun, right? It'd be nice to get some app, I like games partially because they make you do so much. If you write let's say you're writing a calculator program, well, you got to write some buttons and stuff like that handle the mathematics, but that's about as far as it needs to go. Or maybe you're writing a simple word processor and you just need to move text around, edit buffers and stuff like that. Well, that's as far as it really needs to go. But the thing I like about games is that they challenge you. Is like, well, what about sound? What if you want to play with other people? How do you interact with controllers that are not like mice and keyboards? And there's I like how they tie in lots of different kinds of areas in computer science. So it's definitely one of those, I guess, big computer graphics fields. Okay, so any questions so far? Okay, so let's spend a few minutes to talk about a few different areas. So we can kind of look at the different fields of study. And one way of breaking that down is, you have your fundamental stuff. This is simple. How do we understand color? How do we perceive things on a computer screen? Then you have modeling, which is, how do you create actual 3D content that you have to work with? Rendering. And we're all kind of touching on, you could take a lot of these ideas that we put on the board and kind of throw it into these different main categories. Okay, people can spend their whole careers just focusing on just one of these elements. Okay, they have a lot of depth to them. All right, so let's start talking about what are things that you might focus on when it comes to fundamentals, right? These are things we're going to try to tackle, I guess, fairly quickly in the course. So media applications, right? That's one of those terms I threw out there, but I don't expect anybody to understand it. Does anybody want to take a stab at what do you think I mean by media applications? Yeah. Well, no, you bring up a good point, because I saw this description, media applications, and I intentionally took the parentheses off the end. What it's talking about. And the other way to think about media is what you use to express the idea with. Is it an image? Is it sound? That kind of media. Almost like a painter might, use oil as their media, or watercolor, or maybe they're using different kinds of materials. The media is what you use to present the information with. Okay. So all different kinds of applications. So that's another thing about computer graphics, is it's like, okay, doesn't just mean graphics, things you see. It's anything that more or less has a measurement associated with it. All right. So for that point, we want to understand how analog data is digitized and how we can use it to represent analog signals. And, at what point do we not even perceive that it's not real anymore, right? So we'll give for instance, a video, movies. How many frames per second does it take effectively to trick your brain into thinking that what you're seeing is not just one image after the other? Anybody know the magic number there? Yeah, some people can tell the difference at 120. The general number is 24. So a lot of movies are filmed in 24 frames per second. So it's more or less that most people don't know the difference at 24. Now, it's almost the same reason too that, you know, a lot of people can't tell the difference between standard definition television and high definition television because, but most people can if you tell them where to look. Like if you say that pixel right there, watch that one pixel, and then you'll notice, you know, the difference that this new technology makes. But if you're just kind of absorbed into it, you know, I don't know, growing up in the 90s or so, you know, I had an old fashioned television set, and, you know, I will give you this, that there's no way that I would say that it looks high quality nowadays. But, you know, back then it's like, looks good to me, you know? So we get used to, new standards, right? So for a long time, we're all perfectly fine with 1080p on our televisions, and now we have 4K, and yes, you can tell the difference from 4K and like, you know, the standard HD, but, you know, most of the time you're not really thinking about that. If the story is good enough, you don't really care how it comes across, unless you're actually, the story you're interested in is in the resolution, right? It's kind of like people who like audiophiles. They want like the best equipment, you know, to accurately reproduce the audio that they're listening to. And they'll argue about things that most normal people will be like, will be perfectly happy just listening to on their phone, you know, like that's my song, you know. And for most people, they're like, okay, I'm not listening to the song because I'm trying to pick out a detail that my speaker isn't reproducing. They're just listening to the song because it makes them feel good, right? So same idea here is that, you know, human perception is one of those things where, yes, there are always people who they notice something because they're in tune with that. But, you know, what are some what are some limits that are generally well accepted? Like you would never produce a movie 15 frames per second just because it's just not going to work out very well. People will know the difference, just regular people. So you have to go at least 24 or 30, you know, generally speaking. But then if you're doing games, and a lot of people are used to seeing high frame rates in games, then yeah, they might notice the difference between 30 and 60. And so you have to know who your audience is and what you're trying to communicate. Some of the fundamentals include standard APIs. You know, this is like knowing, okay, anybody not heard of DirectX? All right, I'm pretty sure everybody's heard of DirectX. Most people have probably heard of Vulkan or OpenGL or some popular API. In some audiences, you know, maybe all they know is like Unreal or Unity, you know, as a way of, that's how they do their graphics or something. All right. In a graphics class, that we'd want you to be, or from a programming perspective, we'd want you to be familiar with what are the main tools that you would use to do graphics on a computer. Then you have standard media formats. And this kind of goes more into what you're talking about. Is this a JPEG or a PNG? What's the difference between lossy and lossless storage mediums and so on? Color models. So, for instance, let's just see. How many people know that when you print something out on paper in color, it doesn't print in red, green, and blue? Okay, a few people. Does anybody know the colors that the printers use to print? Yellow. Yeah. So yeah, cyan, magenta, and yellow. All right. So color models is just like understanding the idea behind subtractive color models and additive color models. So like computer screens are additive. So you mix red, green, and blue, and you see white, for instance. However, if you mix cyan, magenta, and yellow on a piece of paper, then it's going to look black because it's actually absorbing the opposite color. All right. It's kind of weird, but we'll talk about that. Understanding the trade-offs between storing and recomputing data. Does anybody have an opinion about recomputing data? Just recalculate it. or should you pre-compute it? Depends. Here's a for instance. Fonts are a form of recomputing data. You store a program essentially that says how to draw the letter R or the letter T. And then that way you can draw it at any size that you want. Whereas if you had stored it in a regular raster graphic, if you were to scale it up, then you'd see all the pixels. Okay. But maybe for a photograph that you take with your phone, there's no good way of storing that as shape data. You can't just say, well, there's the circles and the squares and all that. It just would not, there are some ways you can compress, a photograph, but a photograph is better represented with a raster image of just high enough quality. And most of the time you can stretch it and so on, and you don't perceive any difference to it. Okay. So there are trade-offs, right? How big it is versus whether you can just recompute it on the fly. And this is even a thing with, if you're trying to get performance. So in the past, you may just use a lookup table to kind of do this, maybe a complicated mathematical function. You save it in a table and you just look it up in the table. Nowadays, things are so fast, you might just compute it on the fly and there's no need to save that data. You just, I have time, I can just calculate it. All right. Animation, that's another fundamental that we'll cover a little bit more on Wednesday, but we'll also talk about it in depth later on in the course. And then double buffering. This is kind of like a bonus fundamental thing. This is drawing the image before you display it to the user so that you don't have things like tearing. You can, if you're drawing the screen, anybody's seen a screen draw slowly from top to bottom? Double buffering does that in the background, and then they show you the image. All right. And if you're talking about high frame rates, you can tell the difference. It'll look like, half of one screen and half of the next, and it looks weird. Okay. So then we have the next area, which is basic rendering. And these are the kinds of things we're going to focus on in this class. For example, rendering in nature. And what I mean by that is, how does light actually work? When photons bounce around a room, what are they actually doing? All right, forward and backward rendering. So this is an approach of, do you render from the viewpoint of the person, or do you render from the viewpoint starting out with the lights? There's two ways of approaching the problem. Polygonal representation. So, how do you just like you take a photograph of something? How do you represent an object in 3 dimensions so you can put it in at any angle? And so we'd like to be able to represent things with triangles. Basic radiometry or radiometry. Radiometry is basically, what kinds of, are we talking lumens, watts? What physical properties are we actually talking about? Because they make a big difference. All right, let's see here. It's 4:30. Let's take a quick minute to stretch. Like stand up, bend your legs a little bit. You've been bending them, but let's just take a quick minute to stretch, because I can tell that late afternoon is even I'm looking at the list, and the fundamentals seem more interesting than the basic rendering terms, even though I like all this stuff is cool to me. Okay. All right. So transformations. So transformations is basically, how do you do the math that moves your objects around in space? So this is where it helps to understand what a matrix is, what a vector is. If you're doing a lot of animation, understanding what quaternions are is also very important. Some 3D some like Unity, for example, uses quaternions, and they don't shy away from the fact that they use them. And quaternions are kind of an interesting. I think they're very interesting mathematical tools, but they're also kind of like strange because it's using imaginary numbers essentially to kind of work out how things rotate in 3D space. We're going to talk about quaternions in the next 2 weeks, along with matrices and vectors. Projection models. All right. So somebody mentioned that they, were curious about how do you do, projection. So it's actually kind of funny. When I was in high school in the 9th grade, I signed up to take the computer science 1 course at the school I was going to, and they were going to learn C++. And I was in the computer lab, and this was 1995. So this is when Doom was out. All right. And I saw these guys, and they must have been juniors and seniors in high school, and they had wrote this Raycaster. So they were just kind of, it's kind of like Wolfenstein 3D, but no textures or anything. But they were just moving around, zipping around this 3D environment that they had made from scratch. And I was like, couldn't help myself. I went up, it's like, okay, how do you do that? Because before that, I'm in middle school, and at home, I'm like sitting down trying to figure out, how do you do 3D? Like, how do you make a 3D thing look 3D in 2-dimension? I was really trying to like work this problem out in my mind. And I never forget, the one guy says, you just divide by Z. And I was like, that's interesting. I didn't 100% understand what he meant. But, essentially the projection part is actually really interesting, because if you want to take X, Y, and Z and turn it into 2D, then you just get X over Z and Y over Z. And, Z over Z is just 1. And I'll never forget that was it. That was all the math that I needed to know to turn something that was 3D into 2 dimensions. And I was like, mind blown. So I asked him, it's like, what classes did you guys take? And he's like, I took assembly language. I was like, okay, I'm in. So I dropped the C++ course, and I started taking assembly language. And I was like, okay, I'm going to go as low level as I need to, so I can, kind of work on this stuff. And that was a big game changer for me, though. Just knowing like the one obstacle that was in my way of producing something I wanted to make for such a long time. And so that's the quick trick over there. But we're going to talk about how do you actually do it, in context of a modern 3D graphics API. All right. But that was all. Projecting was just divide by Z. All right. And you can work that out on paper when you go home. Just make a box and then say, what if I take my 3D coordinates and then divide, and you'll see that you get the right shapes. Put it on graph paper. Ray tracing. Ray tracing was, I didn't really learn ray tracing for a long time. And I didn't write my first ray tracer until a couple of years ago. I knew how they worked, but it was kind of like intimidating, because it's like, okay, how do you write a ray tracer? Ray tracers are very different than dealing with polygons, because the other way of doing 3D graphics essentially is, okay, I have a bunch of triangles, and the main problem you have to solve is what pixels on the screen belong to the triangle you're trying to draw. Okay. And that one was something I was able to do in high school. And that was, when I was doing in high school, you basically had to do everything. I was drawing pixel by pixel. So I wasn't using like OpenGL or Direct 3D. That just really didn't exist. I was just learning how to do it, I'll call it the old fashioned way. And nowadays, though, now that we're jumping back into ray tracing is very much a per pixel kind of technique. But with polygons, more or less, you're just trying to, you can kind of figure out the lines for a triangle, and you just kind of step through the pixels along the line. One algorithm for doing that is called Bresenham's algorithm, which is a type of 3D differential analyzer, 3DDA, is one way of talking about it. But, more or less, you can kind of decide what pixels belong to the triangle, and then you just kind of fill it in. All right, pretty straightforward. And ray tracing is all about, okay, how do I, find out what objects that you shoot rays. Ray is a type of, it's like a vector that has a starting point. Okay. So you put all the normal way of doing it is backward ray tracing. So you start at the camera and you work your way into the scene and you shoot all these rays out and you find out what objects do they intersect and you take the closest one. Because if I were to shoot a ray, straight through this room, it might intersect many different kinds of objects. And I'm more or less interested in what is the closest one to my camera. And then that's the one I'm going to then base my next ray off of. And so ray tracing kind of solves this next problem, which is visibility and occlusion, which is what objects are behind, or how do I sort the objects in a scene so that I don't have far away objects overlapping front objects. All right. And think about a painter, he's, Bob Ross, right? He's painting and he always starts with the background. What does the sky look like? What do the mountains look like? Before he starts bringing in foreground elements. Okay. And so visibility and occlusion has to do with, okay, let's go ahead and figure out what's closer. All right. We talked about triangle rasterization, shader-based APIs. This is cool. This is really cool. And the reason why it's cool is because everybody's seen Toy Story or some version of it, I'm sure, by this point. Okay. And one of the cool things they were able to do with their RenderMan technology was for every texture and every surface element, they could actually write a little program that says, how do I shade this? Do I apply like flat shading to it? Do I apply some kind of specular shading so it looks shiny? And you could actually write a computer program that deals with all the pixels. But if you can imagine, this is not exactly practical for most 3D applications until really the last 10, 15 years. And more like the last 10 years, you can actually write general purpose programs. And so this basically says, instead of you having to use what's called a fixed function API, where we say, this is how all the lighting is going to look. This is how, if there's shadow support, this is how they're going to look. It lets you do all that. And so now you can do things like non-photorealistic rendering. You can make things look like cartoons and all sorts of things without being tied into like one person's interpretation of what the world should look like. And if you notice the games nowadays look amazing, that's because we use shaders. We do all the programming ourselves to say, here's how objects should look. All right. Okay. And we got things like spatial data structures, sampling and anti-aliasing, scene graphs, and the graphics pipeline. We're going to talk more about those in the next couple of days, so I'm not going to go too much detail there. Let's talk about geometric modeling. So right away, when you look at this, it looks almost completely different than the last one. The most we saw in the last one was, polygonal representations, but polygons only get you so far. The world is not made of just perfect triangles all over the place. We have smooth shapes, all the chairs in here. Polygons would not do them very good justice, I think. We all like things that are like curved. So geometric modeling is really, it tackles the problem from like one of two methods, like treat everything like a solid. So if you're like in engineering, you want to design a new part. Well, you want the program to treat the object you're designing as if it's made out of something, and that you're using like general tools like computer-aided milling or something like that. You need to know how it's going to actually change a raw block of wood or a raw block of steel or something and shape it into the object you want. And then there's what's called a surface-based approach, which is how most of us, 3D games all use a surface base. Anybody seen a 3D game where cloth doesn't like just randomly go through their bodies, or they bend their elbow and suddenly their forearm and their biceps are like intersecting each other? Anybody? And that's because we use surface-based techniques for those because it's faster. But those kinds of details like make the difference. You go to a movie and you see that and you're like, they could have spent a few more minutes just making sure that didn't happen, but all those use surface-based approaches, and there's different applications. Like I said, engineering is different. than say the entertainment industry. Okay, and even the medical biomedical imaging. You might have need to use 3-dimensional blocks of data, and use an algorithm like marching cubes to go ahead and create a 3D representation then that you can look at on your computer. And there's additional things like, okay, if you had, say, some biomedical data, how do you decide where the heart is inside that block of data? Because it's just a giant rectangular block of RGB data or monochromatic data or whatever it recorded. So, there's lots of techniques of how do I decide what's the bone, what's muscle tissue, what's a blood vessel, how do you separate those things out so you can actually take an MRI and or a CAT scan and interpret it. Some of these techniques, they're geometrical modeling, but you don't realize that they actually have applications in rendering as well. So like Delaney triangulation, for instance, that's been used for to make Voronoi diagrams, but it's basically a way of dividing space so that you can't have any smaller volume of data. And so some 3D renderers like Unity will use that kind of a representation of the world to kind of decide how it should store light probes inside the world, so then it can figure out what lighting should be on a character that's nearby that particular area in 3D space. One of my favorites here is called constructive solid geometry. And that's where you kind of start out with a block, a cube, and you say, what happens if I subtract a sphere out of this? What happens to it? Or what if I take several different kinds of objects, and what object results if I take the union? So use set operations so that you can kind of think about objects as like a composite, but that way they don't have geometry just dangling in the middle, in what should be the empty space in there. So constructive solid geometry is very useful for computer-aided design and so on. And then procedural models. So can I make a tree look like a real tree without having to actual scan an actual tree? So can you create rules that you can then apply geometric principles to generate them? Okay, then you get into advanced rendering. I like to say this is my forte. This is what I spent the most of my time really focusing on. And we got some fun. This is more on the physics-based side of computer graphics, where we're trying to actually understand how light is really working inside of a 3D environment. So, for instance, one of the things that I thought was cool when I was doing research on advanced rendering is where it kind of comes from. So, for example, in the 1940s, we're trying to figure out how to make nuclear bombs at Los Alamos National Labs, and they needed a way. They didn't have. It's not like they could just say, "Oh yeah, just grab your iPhone out or a supercomputer and just do calculations." And so they have to figure out, well, how do you decide where neutrons are going? Without actually making a bomb and blowing it up. How do you know that the stuff's going to work before you do it? And so they did all this work on neutron transport, and which is kind of funny, because then a few decades later, when they're trying to figure out how do you generate a realistic computer image, it turns out you can use the same physical concepts of neutrons moving around and just say, well, we could apply this to light as well. And so you take neutron transport theory, and now it becomes light transport theory. And now you have things like path tracing, where you can generate some really realistic images using the power of Monte Carlo methods, which are essentially how can you use random numbers to simulate a physical process without being exhaustive about it. And so it's pretty interesting ideas there. But it covers some of the more advanced things like, basic rendering. We might talk about simple kinds of lights like point light sources. But, anytime you decide, well, what about these kinds of lights? These are not simple kinds of lights that you can just simulate in a 3D environment. There is no easy closed form solution for simulating a light of this type inside this room. So you'd actually have to use some kind of random sampling to kind of figure out, well, okay, the light's going to come from that part of the light and bounce on that wall. And you just kind of take the average of what happens with that. All right. Another element of this is like non-photorealistic rendering, so cartoon rendering. All right, we'll talk about cartoon rendering. I think we'll have some time to talk about that in this course. How do you make things look stylized? Visualization is kind of a big element of computer graphics. We'll talk about in just a moment. All right, so subsurface scattering. Everybody noticed that people that are simulated on screen look better than they ever have before, and one of the reasons is because when light hits your skin, it's not like it just reflects off the surface and that's it. It actually goes in, bounces around before it comes out, and so if you ignore things like how light interacts inside skin, then you can't get a realistic rendering of a person. It's just not going to happen. Okay, computer animation. Yet again, we have completely different kinds of words, different kinds of lingo, right? So computer animation involves like kinematics, inverse kinematics, forward kinematics. If you could just imagine a robot, if you're trying to plan how a robot arm should like move so it can pick up a part, it's a complicated system. The more joints you stick on a robot, the more motions it can make to get to one particular orientation. And is that the best orientation? Or maybe you're trying to simulate a rag doll, and you just like to be able to grab a character's arm and just say, well, we want to reach up to the cupboard. So you just grab the hand and put it up to the cupboard and have, how does the computer know how to move the other parts of the arm so that it looks realistic, right? Collision detection and response, right? So we'd like to be able to know whether objects hit each other so that they can behave naturally. And you can either be rigid about it, like the billiard ball kind of model. Well, if you're just doing like a billiard ball model, well, what about things that are squishy? Lots of things in life kind of have some give to it. If you throw something on top of a bed, you don't expect it to go thud. You expect it kind of like fluff, like, it looks fluffy. You expect it to act fluffy as well. All right. There's some interesting procedural animation things like voids. Anybody heard of the voids? That's kind of like flocking behavior. How do you create rules for like several objects to kind of move around? Crowds. Remember watching Lord of the Rings? Crowds were kind of a big thing there. How do you how do you make a large group of crowds look like they're all individuals and not just like one robot army, and that's getting better all the time. Particle systems, how do you like rain? Rain could be a good example. Do you actually like manually animate every single, drop of rain, or can you like create a system to automatically generate those? All right. Physics-based motions. We're not really going to get too much into that. We actually have a class here that I taught last spring. We talked about physically based animation. So hopefully we get to offer that again next year. But, we kind of go into a lot of these kinds of things, particle systems, physical motion, fluids. Motion capture is one of these elements that's really big. How can you create convincing performances using people? And then on top of that, this is a big field in AI is kind of, how do you take previously captured motion capture and then like interpret it in a new context, right? So if you have a video, say of motion capture of an actress running around a 3D environment, well, can you take that data, right? It's still kind of discrete, and so you capture her running around a square environment, but how can you turn it so that it looks like she's running around in a jungle and it looks realistic, right? Because you can't just go do motion capture in a jungle, So there's a lot of areas in computer animation that are still kind of at the forefront. How do we solve these kinds of problems? All right. We'll probably talk about keyframe animation in this course because it's kind of one of the basic things. All right, and then we have a visualization. So anybody been to like a really nice museum presentation or a planetarium, maybe, or watched a documentary on TV about, some kind of, we're going to imagine what the Orion Nebula looks like. So we make a computer animation of that visualization so we can kind of communicate to somebody. I mean, how do you experience a nebula in your living room? That's kind of a strange concept. I have a telescope. I've looked at a nebula in a telescope. It does not look like the pictures. It looks, kind of faint and fuzzy, and it doesn't, so when you watch like a visualization of one, like, whoa, this is interesting. You almost like touch the gas fields, so I think that's interesting. Or how do you, we all use visualization like weather patterns. I lived in Florida for a few years before I moved out here. Occasionally we'd have hurricanes, right? So you'd see computer models of saying, well, we think it's going to go this way, or it might go this way, right? And so visualization is used to kind of communicate that kind of information to people. So there's a valid need. Like somebody in here mentioned sports. I think somebody in here mentioned sports. So like, how do you figure out what the trajectory of a ball is going to be? You show like a pitcher throw a ball and you're like, this is how it flew down to the catcher, and that's how we know it was a strike. So you can kind of get statistics on people, but we use this kind of stuff all the time to kind of tell a story. And or it's like or football, the John Madden days where you write on the screen, this is where it went. But now we can use visualization to kind of say, yep, this is where the 10-yard line is, or you name it. Visualization. How do you communicate ideas to people? Okay, so that's what I had prepared in terms of content for today. Just kind of talking about all the different areas in computer graphics. You notice that we didn't get through every category. Computational geometry, machine vision, image processing, although we are going to cover a little bit of image processing in this course to kind of talk about computer vision. But computational geometry, these are problems that you solve regarding geometry. For example, one of the biggest problems that you may come across computer graphics is convex hull problem. You might have a bunch of points. What's the smallest convex shape that fits around those points? That's a problem that I've seen in my study of computer graphics, right? And it'd be surprising, it touches a lot of different fields, machine vision, image processing. So if you have a robot, how do you, we're talking about automated cars, self-driving cars. Well, how does the car know where all the other cars are in relationship to it? Or, does it, maybe something pulls out in front, like if a robot's maneuvering your kitchen, right? And you decide you're going to open up the cabinet, it should be watching for things like that. So it doesn't just like bump its head. Anybody ever open up something high and you weren't paying attention? Whack. Those are, even we have, human vision problems when it comes to stuff like that. We were walking down with our phones and we don't notice a potential hazard. So, lots of different areas. I didn't specifically mention human-computer interaction on here, but I have some. I actually got to earlier this year got to meet. Let's see here. Was it Van Damme? There's a classic book on computer graphics, Principles and Practice, by Foley, Van Damme, and I'm trying to remember his first name. Share web browser. James Foley. So pretty cool guy, and he's actually No. That's looks different. I'm not so sure that's might not be him. I know where to find it. That's I went to the now I'm having a mental block here. Andy Van Dam. Okay, that's what I'm looking for. Anyways, Andy Van Dam is find a picture of him real quick. There we go, right there in the middle, Andy Van Dam, and he's done a lot of work in human-computer interaction, and he shared a few things at a computer conference I went to. It's a 3D graphics computer conference over in Montreal this last year, and he showed some really fun stuff about computer graphics ideas that we have not yet seen happen. Killer applications that if any one of you solved those problems, you'd be like, probably on your way to some kind of prestigious award, some sort. Things that we would like to do with our computers that we still cannot do today. We're getting closer, but when you look at some of the ideas that people have had, or we'd like to do this, and you notice that we're not there yet. So I hope to kind of share with you some of that next time on Wednesday. Some of these other ideas, show you some interesting videos of interesting ways of interacting with the computer. So hopefully everybody enjoyed the course today, and I'm going to go ahead and stop the stream. So thank you for everybody who joined us on Zoom. Let me see where.